Hi, my name is Kathy, and I would like to present to you fixing Wikipedia interlinks using revision history pattern, a joint work with Tova Milov from Tel Aviv University and Slava Novgorodov from eBay. Maintaining correctness of Wikipedia interlinks that point from one article to another is challenging. The challenges are that different Wikipedia pages are often edited by different people that sometimes are not aware of each other, and that consistency constraints on Wikipedia interlinks are often soft and need not always be applied. An example could be Neymar, a soccer player that plays in Barcelona, his team, and then he is being transferred to another team. So what happens is that he no longer points to Barcelona, but Barcelona still points towards him. So one might think that a possible constraint over the corresponding knowledge base may state that if player A links to club B, then club B also links to player A. But there are several drawbacks to applying this approach as comprehensive solution. The most crucial drawback relates to the fact that the constraints are static and lack any temporal dimension. They don't account for the time window during which partial edits are acceptable, and in some cases practically unavoidable. Inconsistency should be resolved at the earliest appropriate moment, but not earlier. Wikipedia updates often follow desirable patterns and leads to consistent state. So what our algorithm does is that it's identified relevant edit pattern across revision history of Wikipedia entities of the same or other related types, along with the time window in which partial edits are tolerable. To do that, we model Wikipedia as a graph. Each entity will now be a node in the graph, and each link connecting two entities will now be the edge. We use type hierarchy that is provided by Wikipedia, so each node has a specific type. We address the edits as action, so we could add new edges or delete existing ones. And we make a pre-processing to get reduced set of actions that won't include actions that being canceled later on. Another thing that we have to do is we have to make an abstraction. So we will generalize a set of actions involving specific entities to general patterns over the corresponding entity types. So now we won't look at specific soccer players, but we will look at the whole group of soccer players. Then we define pattern as a set of abstract action. As you can see that pattern number 1 is more specific than pattern number 2. They both are in tables on the left side. And on the right side, you can see the realization of that pattern, which is the specific entities in Wikipedia that follow that pattern. In our example, specific soccer players that left that team, and here they are in the table. Wikipedia is large and lots of things happen on the same time and they're not necessarily connected. So we have to ensure that our patterns are connected, so the patterns will be meaningful. We will have to make sure that the patterns that we look at are reachable from our starting point, which is the type that we get as an input. Here it's a soccer player, and the table on the left is a set of actions that abstract actions that are part of a pattern that is displayed here as a graph. The last thing that we will have to define is frequency of a pattern. In our definition, it's the portion of entities from that specific type that follow that pattern out of all existing entities of that type. Here, for example, you can see two distinct soccer players that follow that pattern. The main stages of our algorithm is the first one is in the initialization. So we get type as an input, default window size and threshold. We then get all the entities from that type. We split timeline into time windows and then extract the relevant action performed within each of the time frame. We keep abstract actions and their realizations per window, and we implement it as relational tables, as you can see here in the example on the right. And we output for each window patterns of size 1 that are above the threshold frequency. The second stage is the refinement stage. We alternate between the refining the entity sets that we consider and refining the considered window width and the frequency threshold. We extend the considered entity set to include all entities of the types occurring in patterns in our time window. We add the revision history that happened within that window, and we now consider them by mining the extended set of actions for frequent patterns. In addition to that, we examine the effect of extending our window's boundaries and lowering our frequency threshold. The last part of our algorithm is mining connected patterns. So given a specific pattern, we try to extend it by adding new edges to it. After adding another edge, we calculate the frequency of the extended pattern. We do that by join between realization, the one that was of that pattern, and the realization of the new edge that we have added. And then we keep the one that exceeds the threshold. We repeat that until frequent patterns are identified. We could use our algorithm for cleaning tasks. More details could be found in our full paper. And in our experiments, we compare our algorithm to other two baselines that are versions of our algorithm. The first one is without making join between the realization tables and just calculating naively the frequency of each pattern. And the second baseline is our algorithm, but without increasing the examined graph gradually, but just looking at the whole graph at once. As you can see that those optimizations reduce the running time significantly. And another experiment that we've conducted is of parallelism of our algorithm that performs much better when it's run over multi-core architecture. So to conclude, our model is a Wikipedia plugin assisting editors in maintaining the correctness of interlinks. Our efficient, highly parallelizable algorithm identifies relevant edit patterns across revision history of entities of related types, along with time windows in which partial edits are acceptable. Incrementally computed patterns by dedicated relational queries, allowing the use of effective optimization of the SQL engine underlying Wicklin. The discovered pattern and windows are then used by Wicklin to alert editors on past edits that appear incomplete and provide users with online assistance as they update Wikipedia. Our experiments with Wikipedia data demonstrate the efficiency and effectiveness of our approach in identifying and correcting errors. Thank you very much.